Okay, greetings students. As you can tell, I have my book and uh, um, this is actually one of the files I just uploaded to Canvas. It's a file I've actually given out in class. I gave out in class earlier. At the time I called it the test bank. It can't really be a test bank anymore because the only way for an example to come from our textbook to an exam would be for me to type it. So since I'm not the one typing our exams, I'm selecting questions from the homework. I had to rename these. I guess I'm going to call them talking points. So when you look at the book, these are still the key points that I want you to be aware of, the key examples. Now, I'm skipping chapter 1. We've already covered chapter 1 in class. So here we are in chapter 2, and you can see what it says here. 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, and then this preview of 8.1. So I still want to do that because this will help you with the homework that's associated with this topic. So if I go to this other window here, this is our book. Now the book on the screen is a little pixely here, so I have my book here. The lighting is not terribly good here in the office, but I'm going to make the best of it. All right, so in 2.1, I'm looking at my list here, it says that we should know examples or cover examples 4 and 5. So you really can, especially in this section, completely skip any example that's not on the list. So section 2.1, example 1, I would say don't even bother reading these. Example 2, here we are. Example 3, this lady is very good. All right, example 4. All right, example 4 is an example I do want to talk about, and it's a really quick one. The question, and hopefully you're seeing this, on your own in some way. I mean, filming the book cannot be a strategy moving forward, but it says to identify the domain and range of a relation. So it's well illustrated. It says here that the range is these values here along the y-axis. It should be going here along the y-axis, and the domain are these values along the x-axis. Well, let's talk about the range. The minimum y value is 4 because of this ordered pair 0, 4, and a maximum y value, the minimum y value is -4, and a maximum y value is 4. Now, the best way to write that is in interval notation, which we have covered back in chapter 1. The way interval notation works is the minimum, comma, the maximum. So interval notation, it's not the only way to write it. They also wrote it in set notation over here, but I like the idea of interval notation just being exactly what we see. It's the minimum followed by the maximum. On the x-axis for this illustration, it would be the minimum, -9, and the maximum, +9. So let's look at that again. So your job is to look at this, treat it like a number line. What's the minimum x value? What's the maximum x value? And that's the domain of that function. Example 5 is the only other example in that section that's going to be part of our talking points. And basically this is just done by point plotting. Again, point plotting is something we did earlier. We did point plotting with lines and graphs on our first day handout, but this is just the book's way of doing it. So the book will pick x values, calculate the y values, and plot those points. I don't know how much students learn by just looking at a completely computer-generated image of a graph. I don't know if I was trying to learn how to draw anything. Looking at a perfect picture of it might not be the best way to learn how to draw. So just looking at a computer-generated image might not be your best bet. So do try to do these, and there are videos online which I'll link as well that show this process. But you're plotting points, and then you're drawing the correct shape through those points. And this is just one of our 3 shapes. We only have 3 shapes that we're going to have to draw, and even that's different now that we're doing the things on the computer. So in the regular semester, I only had you draw 3 shapes: lines, parabolas, which is what this is, and circles. So this shape over here, it has a name. It's called an ellipse, but you don't have to draw that shape. It was already drawn for you, and you just were supposed to look at that image. All right, so that's it for 2.1. 2.2 has just 2 examples listed as well, or 3 examples it looks like, 5, 6, and 7. So when you get to section 2.2, once again, you can ignore these little diagrams here. And let's get to the important stuff. Example 5. So example 5, I honestly don't know if it's better for me to film it up from my book or my computer screen. Oh well. Example 5. Use the vertical line test to identify the graphs of the functions. So the way this works is, if it's a function, it's going to pass this thing called the vertical line test. A vertical line will intersect it at most 1 time. So all of these are functions, except for this one. This one doesn't pass the vertical line test because this vertical line hits the function twice. So whatever this is, it's called a relation, which is a larger group of things than functions, but it's not a function. That's all I wanted you to say. Is it a function? Is it not a function? And the answer is no. Example 6, pretty straightforward. I'm going to have you go ahead and do that. Well, let's just look at one here. I'll point to one here. So they give you a function, and one of the key things I'm going to talk about all semester long, really, is this idea of an argument. So when they say f of x equals 3x minus 6, what they're saying is take whatever the argument is for x, whatever the argument is, or this function, f, takes the argument, multiplies it by 3 over 2, and then subtracts 6. So in this first problem, they're saying f of 10. So the argument is 10. So take the argument, multiply it by 3 over 2, subtract 6, just do the order of operations, and you get the answer. So a fairly straightforward example. Now, it does get pretty interesting when we get to our last example in this section, and that is example 7. If you look at this, I'm not a fan of this function, the way they wrote it, capital F of z. I don't know why they use non-standard notation for us. We can just think of this as f of x, but if f of x equals 4x plus 7, how would we evaluate that? I actually did that over here. So I did it by hand, this problem, but I changed it to f of x equals 4x plus 7. Find f of x plus 3. So that's the more standard way. Instead of a capital F, I used a lowercase f. You can name a function anything, but f, g, and h are usually the typical names we use. Whatever the argument is, we're going to take the argument, multiply it by 4, and add 7. So this time, with these long parentheses here, they're saying the argument is x plus 3. So I did the problem over here. F of x plus 3 means 4 times the argument, x plus 3, plus 7. That's going to give me 4x plus 12, plus 7, which is going to give me 4x plus 19. Now you might notice my little sugar packet here. One of the things I do in lecture typically is I'll say something like, how can we make this problem longer? And that's just a typical thing we do in math. So how do they make this problem longer? This problem, if it had been in chapter 8, it would have started right here, where they gave you f of x equals 4x plus 7. And then instead of already wrapping the parentheses around the argument like this, they would have given you a second function, g of x equals x plus 3. And then the instructions would have looked like this, f circle g of x. That means f is the outside function and g is its argument. So since g of x is x plus 3, I would just take this outside f, copy it, and replace g of x with x plus 3. The work is exactly the same as what we do in chapter 2. It's just a different notation. So I'll flip over to that particular example in the book, and let's see. You can see it. They'll give you a function f of x. This one says take the argument, multiply, square it, and then add 2 times the argument. So whatever you put in there, if you put an x in there, you're going to take x and square it, and 2 and square it. All right. So what are they asking us to do on part A with that little circle there? They're saying f of g of x equals this. Now we know what g of x is. It's 2x plus 1. So we replace it and put it in there. Now what's astounding here is if I cover this up, if I cover that up, I didn't do a very good job covering that. All right. And just start the problem right there on that line that's not covered up at all. It's f of 2x minus 1. That's essentially the same thing as we were doing in chapter 2, when they said f of x plus 3. You just substitute the function and combine terms. The difference here is they're trying to introduce this new function, this new material, or new, well, it won't be new to us because we're already doing it. We're already previewing it back in chapter 2. But they introduced this new idea. So the only thing that makes this a chapter 8 question is instead of starting it here, they started it here. F of g of x, and then it's our job to put the argument in the function and then continue the work just like we learned to do in chapter 2. So that's why we're previewing that topic. We don't have a lot of questions on that topic in chapter 2, but we have a few. All right, and that's 2.2. 2.3 is another very quick section. Chapters 2 and 5, examples 2 and 5. So example 2. You know what, I was gonna switch to using the computer, but now I'll stay with this. All right. So they give you a function and they ask you to find the domain and range and the intercepts this time. So domain would be the minimum value of x and the maximum value of x. Now this thing just keeps on getting wider and wider, so the domain is from, in interval notation, negative infinity to infinity, like they wrote here. There is no minimum value of x, it's infinite, or you can just think of the arrow going on forever, and then another arrow on this side. Now the range is kind of interesting. The minimum is negative infinity, but the maximum happens at this point right here. So the maximum y value is 6. So when I wrap that up into interval notation, it's going to look like this. Negative infinity for the minimum, 6 for the maximum, a square bracket to indicate I'm including the 6. Intercepts. Intercepts are where the graph is not in a quadrant, quadrant 1, quadrant 2, quadrant 3, quadrant 4, but actually crosses either the x or y axis. So the x-intercept, we have -3 and 3. We're just reading it like it's a point on a number line. the y-intercept is 0, 6. And so if you're writing the intercepts, especially if you're writing them as ordered pairs, and that's kind of important that you know that, which is the x and which is the y. X is always before the comma, y is always after the comma. So that's how we do that one. This next example, the only other example in this section is example 5. And it kind of goes over the same material in a different way. They say find the zeros of the function, and the zeros of the function, if you have the graph, are really just the zeros of this function here are really just the intercepts, but not expressed as ordered pairs, expressed as the actual number. So these are the numbers without the parentheses wrapped around it that are the zeros. And what that basically means is if the argument is 3, the function would have a value of 0. If the argument is -3, the function would also have a value of 0. That's all there is for 2.3. In 2.4, we only do one problem from our list. Oh, I'm sorry, 2. Examples 1 and 2. So here's 2.4, example 1. Graphing a line. Again, this is something that we've previewed. We've not just previewed, but this was covered in chapter 1. So I don't know why it's here again in chapter 2, but they covered it again in chapter 2, I guess, just to reiterate the idea. But whatever technique you use to graph this, you should be able to graph that. And make sure you can do it using the techniques or the material that you have on the website. Example 2 is asking you to find the 0. Now notice this time they don't give you the graph. So how do you find the 0? You solve the equation by setting it equal to 0. So f of x equals 0 discovers the 0. So you'll see that that's exactly what they did. F of x equals 0 and solved for x. So that's it for 2.4. We only have one example in 2.5, example 6. Actually, on the homework, I say skip example 5, and we really kind of do, but I think that example 6 just kind of gives us this idea of how interval notation works once again. This is going to be a thing that just keeps on coming back. So let's look at the answer. The ultimate answer here is minimum comma maximum. The minimum's -3, the maximum is 1. We don't include those, and you can kind of just see how the process worked. You want to solve for x by doing the same thing to all 3 sides. So in this particular one, to solve for x, they're going to subtract 1 from the inside, the left side, the right side. Going to divide both sides by -4. When you do that, the inequality changes direction. And this is very important. Whenever you write your final inequality or your interval notation, it has to be in number line order. So minimum comma maximum. All right, that's it for chapter 2, except for 2.6. And 2.6 is going to need a video of its own. It is absolute value inequalities, well, absolute value equations and inequalities. And it's all about our favorite word of this chapter, the argument. So it's what I meant when I said our job is to free the argument. Let's just look at a real quick example here. I don't want to really open this up, but this is the argument of the function, just like we were talking about before. Usually it said f of x, but 2x minus 1 is the argument of the function. And our job is to get that 2x minus 1 out of there so we can solve the problem. More on that later. This should get you started on chapter 2, and I hope this was helpful. I will try to find an office with better lighting. Actually, I'm doing this in my office, and I know they're not going to let me come here anymore. So I'll definitely be doing these with better lighting. All right, take care, everybody. Goodbye.